Okay, let's continue our review of control theory and some of the projects which we have done in the ACE lab. I'll show you some videos of experiments you have to do later on, as well as some research projects. So coming back to my station, we were looking at the definition of autonomous control, which is a part of our name on the ACE lab. Autonomous control, this is just my definition, it may be different than many others, is an integration or combination of artificial intelligence with control theory, communication theory, sensor instrumentation, and possibly some other paradigms. So this is potential approach to design a control system which can, by and large, decide on its own what to do, with minimum interference of the human, especially in the deeper space. It takes a long time to be able to communicate to the Earth. So here I define further artificial intelligence. It is what we call soft computing, expert system, and so forth. Some people, like IEEE, calls, in place of soft computing, calls it computational intelligence. Computational intelligence. And you'll see what we mean in a minute. So again, pictorially, autonomous control is the overlapping of all these tools. So what is autonomy? A state or a system is a state of a system is autonomy, or it is autonomous vehicle, if a vehicle or an aircraft or a device would operate on its own without any or minimal interference from the outside world. Okay. So obviously this is a very desirable paradigm when you want to send a system, a device, or a vehicle, or a swarm of vehicles to a distant planet. Okay. Some of you may have watched the movie Martian, so it's a very isolated situation. So what is soft computing or computational intelligence? It's a consortium of different methodologies which work together. Fuzzy logic, which is a tool created by my dear mentor and colleague, Professor Lotfizadeh at UC Berkeley in 1965. We just passed the 50th anniversary of that first paper on fuzzy sets. What fuzzy logic does, it mimics human reasoning. The kind of decisions you make on a daily basis, it can be done on electronics now. As I said, you can design a fuzzy chip. Okay. And neurocomputing is this block. Neurocomputing is based on perceptron and multi-layer perceptron, which is a mathematical modeling of the behavior of the human neurons in the brain. So your brain neurons are mathematically represented by a model of multi-layer perceptron, so to speak. So neural computing or neural networks, by definition, is a tool to learn. The emphasis is the word learn. Fuzzy logic, as I just said, is argues and reasons. So they have different functionalities. Evolution computations, many different tools, genetic algorithms, genetic programming, and many other sub-areas are based on DNA, evolution and DNA. And it's an evolution of survival of the fittest, like law of the jungle. Okay. And you have chromosomes which are reproducing themselves, creating population after population. And they get constantly being evaluated for their fitness, and the weak one goes away, and the strong one remains until you come back. And chaos theory, probabilistic, stochastic learning, automata, all of those are additional tools combined into today's artificial intelligence, or soft computing, or computational intelligence. Probabilistic reasoning, as its grandfathers are expert system, which is the traditional expert system from computer science. They differ from fuzzy logic rules. They have also expert rules here. Their rules are crisp, means you can succeed or fail. There's no other option. In fuzzy, you can partially succeed or partially get by being false. Okay, partial truth, partial false, and so forth. So, in order to use these tools to design a control system, first you need to come up with an engine. We call it expert engine or inference engine. You get input from sensors in your control. You put it into a linguistic term. For example, you may have in this room temperature variations from, let's say, 60 degrees to 80 degrees Fahrenheit, let's say, for the sake of discussion. And this becomes a band or a region in a linguistic term. You say this range of temperature corresponds to various degrees of medium temperature or comfort level temperature. So you put the linguistic variable on a numerical variation of a numerical quantity. And there will be mathematical functions, we call it membership function, which represents a lot of these variation ranges. So you could have minus 100 degrees on one end, Celsius, to plus 100 Celsius. In between, you have numerous different linguistic variables, depending on how you like. For example, if you're from an area of the world which you love humidity and very hot temperature, that's your prerogative. But if you are, in northern Europe, for example, Norway, Sweden, you act differently, okay? Or Alaska. So you change that, we call that fuzzification. You change the numerical data to linguistic data. And it becomes a sequence of membership functions. Then that engineer who was retiring next month, all the information and all the knowledge of that person can now be put into an engine, we call it inference engine. And it's connected in general to a knowledge base. Knowledge is feeding the engine. And then you come up with a decision which is going to be the consequence of your decision. That consequence is still in linguistic term. And you want to bring it back to real world, in a numerical world. We call it defuzzification. And you'll see it in a minute how that works and later on. So fuzzification going from crisp word to fuzzy word, and defuzzification goes to the reverse. This is actually a control system that very often has been built numerously by my students and people everywhere. Here is your desired input that you saw before earlier. Your output is your plant. Here is your controller. We call it fuzzy controller. You come with a sensor information. It's still in a numerical word, and then becomes a given voltage. You go to analog to digital conversion. you converted a given voltage representing your physical output into a bunch of bits, 0, 1 bits in a binary situation. So you come up with so many bit words in the computer, or in the microprocessor, what have you. But even it is in digital form, it's still crisp. Okay, you actually go from crisp to fuzzy through fuzzification, which I just showed you. And now your variable at this stage are linguistic, and it's also inside a digital world. The inference engine acts on the sensor information and gives you a decision, an output, a control signal in fuzzy, in linguistic term. The linguistic term through the fuzzification becomes crisp, and the crisp information in digital form goes through digital to analog conversion, becomes analog signal back to reality, back to the world. Okay? You start from voltage here and you end up with voltage here. This voltage is your control signal which the brand is waiting for you. And you are sampling it in between the samples, you wait, holding the previous value until the new sample comes up. And you move on and loop around. Okay? And some of you hopefully can actually implement that in the lab in this course. You can first learn it to do it on MATLAB, and then you can do it in real time. Neurocontroller, controller based on neural network. Here is a multi-layer neural network or multi-layer perceptron. What you do, you pick up the information from the output, you feed it into the training set. You create a set of input-output tuples, double quantities, input and output together. You basically create a large table of information. And you give that to this multi-layer perceptron. And this multi-layer perceptron learns what that data is trying to do. If the input is x1, your output is y1. And input is x20, your output is y20. And this relationship between domain and range of this unknown function, nonlinear function, which we don't even have any mathematical representation for it. And you have to remember that unlike classical control design, which is model-based, these are all knowledge-based. So now, some of you for the first time are learning a new control paradigm, which is not based on mathematical model, based on knowledge of the plan, which comes from experience that you get. So what happens that this neural network is actually placed like an optimum controller which picks up the real output, and now because it learned the mapping process, it gives you the input, and you run that. This is called neural controller. Now, neural networks until recently has been not very efficient to do control for the following reason. For a very short sampling period, you don't have a fighting chance for the network to be trained fully in that short time. In other words, it can't learn what to do in such a short time, in real time. Okay, you can do it offline, put it into a lookup table, and put it on the system. That's possible. But that's not what you may want to do. But more recently, you have what we call deep architectures and autoencoders, and building up to a new discipline of neural network. Some people call it advanced neural network. But it's also known into a concept called deep learning. Okay? I have graduate students who are now working on deep learning and are predicting the stage of the Alzheimer's disease based on a whole bunch of brains of the patient. Okay? Or you can look at the traffic jam on the highway, and we had a tremendous traffic jam on those of you who were on Interstate 10 today. And predict what is going to be the traffic jam in advance. Okay. So these things are becoming more and more efficient and learn much faster. And deep learning is going to be playing a major role in major IT companies in Silicon Valley and other places, which would allow you to do search engines much more efficiently for image data. Image data. Okay? So that is something coming up, I think, continuously evolving right now. Just like before, you could combine different controllers. And these are many different ways you can create your autonomous control or intelligent control. You can build genetic algorithm coming from evolutionary computation and fuzzy logic. You could have neuro and fuzzy together. Actually, there are fuzzy chips or neuro-fuzzy chips right now, which can learn and reason on the same chip. Okay? And I know Japanese have already done it for years and years. Okay? And I'm sure Europeans and Americans have done that. And to be honest with you, the word fuzzy sounds a little bit awkward, and a lot of people call it something else. If you look at it, if you go shop for a video camera and read into options and into its specification, there is fuzzy logic control on it, but they don't call it that. If you go and look at the maybe low-end, middle-end, even high-end video cameras, shop around, and when it says motion stabilization is on it, that means it's fuzzy logic in it. When you're taking a video and your hand is shaking, you become a bit older than what you are now, you may be hand shaking. Or you may be taking a video in a car, or the car is moving, and you have very difficult way to do. The fuzzy logic rules can distinguish between shaking of your hand or moving in a vehicle versus the movement of the object in front of the camera. So you may have a perfect video from a moving object and still have a shaking hand and still okay because of that. Okay. Last time I checked in the US Patent Office, I visited that at least once. There are at least 25,000 patents in Japan alone on fuzzy logic. Okay, and I'm sure thousands of them here. So you can have adaptive control from classical and modern class, fuzzy in the intelligent class. You could have decentralized control and fuzzy logic and so forth. If you are interested to read more about this, may even be outside the scope of the course, let me know. I know which book to download on my website. Fuzzy neural controller. This was actually the subject of a PhD work of one of my former students, now working for Hitachi. You have a plant here. As we said before, the input and output goes to the neural network, and this block keeps track of, identify a software-based model for this plant. And then there's a bunch of rules here, and this neural network comes and teaches the fuzzy controller rules to change. So you build your own inference engine on the fly. Believe it or not, they did that on a robot in New Mexico. Okay, and the robot was acting very funny at the beginning because there were not too many rules in the engine. But after a short time, it became very smooth and deep. This is a bit, unfortunately, a bit unfocused. It needs fuzzy logic. The camera didn't have fuzzy logic. But this is a group of cooperative robots. This is a multi-agent strategy for automatic guided vehicle, AGV, which you can see in every factory. This happens to be work that was done by a former visiting student of ours in in BGU in Israel, and also worked with another student of mine, right now with the Applied Physics Lab at Johns Hopkins. What you see is a hierarchical behavior fuzzy controller. At the lowest level, at this level, the mobile robot, this is for mobile robot, it can avoid obstacle, it can avoid the kill, it can wander around, okay, randomly. Or you, and this is a degree of applicability, a parameter we added, then you have a safe wandering human. This is the combined or compound control. This is the primitive behavior, this is more advanced behavior. And then the top behavior is safe homing. Okay. Then homing is another approach, constant velocity is another one. So all of these are an extension of the work which was done a long time ago by Professor Rodney Brooks at MIT, but he used express rules. We extended it to fuzzy logic rules. And a couple of PhDs came out of that. And as I said, the gentleman is now at Johns Hopkins, used to be on Mars mission at JPL. This is a scene from the manufacturing lab in BGU by my visiting student, Dr. Sigal Berman. And you can see 3 different robots are wandering around the factory floor. They work together, they communicate together, and they run like what now we call cyber-physical system. So their behavior, at the lowest level, they have different behaviors, and they use it accordingly. This is another autonomous control of water treatment plant, which we built in New Mexico, at University of New Mexico, by a combination of a mechanical and 2 electrical engineering students. You have the brine, in this goes into the heat exchanger, and it goes to this what we call flight chamber, and it becomes sweet water, from gas to liquid, and then get collected in here. And this is the part of the fuzzy logic controller. They built attached it to the wall. This whole system was a single-stage flash desalination plant, where you see them now. Soon you're going to see them everywhere in the world. Just see how much scarce of water we have. Everybody is worrying about converting their meadows and others to deserts in due time, unfortunately. So we have to take water from the ocean and convert it into potable water. And my PhD student actually, during the defense, actually drank from his own factory water. Okay, I let him drink. Okay, this is the control. This is the flight chamber. This is not UTSA. A few years ago, I was part of a team of professors and students, which we put a solar system on the main campus, 1604, and the campus downtown. This is the top of the, I think, HEB Center, University Center. If you go upstairs, you may be able to actually see that. This is one which is on the floor of the same system from a different angle. This is on the old engineering building, the second one. If you go to the 4th floor of BSc building, going through a window, you can see all these panels. Here is a neural network, a sensor network, a real one, sitting on the campus right now, who's part of our project. You have many different sensors. You have wireless node, you have inverters, and you have gateways, and you have weather station and so forth. And in real time, the data from these solar systems are being gathered, put on a website in real time on campus. Okay. Of course, we built that to become a part of infrastructure of the university. This is not for research. We just got a state funding to add that to this particular way. And altogether about $2.5 million, and it's saving university around $65,000 per year. Less cost for energy. Because the smart meters on this, these are some smart meters, when the university is shut down, like during Christmas break, the energy produced is sold back to CPS Energy. Reducing your bill. Okay. You could do that in your home. Here is a block diagram of a proposal which we wrote with many colleagues at Texas Sustainable Energy Research Institute. You have solar system, and you have inverter, you have storage, you have controllers, monitoring station, and so forth and so on. One of the big issues of solar energy, wind energy, tidal energy, and so forth, they all depend some aspects of the nature, of the mother nature. But you can't count on mother nature to deliver sunshine to you every day. So it's called intermittency. Okay. One of my PhD students who's now working for a local industry here, he created a forecasting engine which gives a company like CPS Energy a potential prediction of how much solar energy, kilowatt hour, megawatt hour you're going to have the next 24 hours. Okay? And that's a big deal because they need to make advanced decision how much to sell or buy to take care of our daily lives, because we can't wait for electricity. We want it now. We have to take it for granted all the time. So that particular one is, as we speak, is being patented here, and we hopefully can, after that, we can start licensing it to hopefully utility companies around the country. And here's a concept called microgrid. I believe one of my colleagues, Dr. Hari, who used to be where ACE Lab number 2 is, moved his solar and load and other emulators all to his lab in AET building, another building here on campus, and created hopefully a microgrid. And if you have energy in your own home, someday you may very well have that, put solar panels on the roof, you bring it down to the house and run your appliances. You also connect it through the smart meter to the local grid. You go on vacation, you come back, and you get positive instead of negative in your bill. That's called microgrid. A company called Concert, which is in town, they go around and with the help of General Electric, they add a gadget to your regular appliances, legacy appliances, make them into interoperable. So you can control them all together as a smart home. A smart home is like that. And here is a humanoid robot, which is what Mr. Errol has done, and we show you a video of it next time. This is the cloud computing, again, open cloud stack of the university. Final note, you can have several different paradigms. You can have classical, optimal, decentralized, adaptive, fuzzy logic, man-machine approach, where you have actually human in the loop. You cannot ever replace human, for sure. The intelligence of the human and reasoning and always is there. Anything else is a mimicry of the human. Okay. As I said, some approaches are robust, have beautiful theory, but little right now applications that I can tell. I may be wrong. Well, fuzzy logic, for example, have applied extensively, but need more solid theories like stability. Cloud media is becoming a key venue for large computing, such as image-based control. In fact, some of the projects on the visual SLAM, if you take it, you will learn how to use image processing on the cloud, bring it to the robot in the lab, and run the robot. Image-based control. Okay, so I'm going to stop here, and then I'll show you a video the next part.